So welcome. We want to discuss the absolute convergence and how to do that using ratio and root test. So the motivation should be the following problem. We have this problem here, which is n 2 to the power n divided by n factorial summation I going from n going from 1 to infinity. Now note that first of all, to do this problem, if you want to use comparison test, you will have, there's no straightforward comparison yet, all right? In that case, you will have to compare 2 to the n and n factorial and then work it out, okay? So we'll develop a new technique on how to basically look at the convergence or divergence of the series. So, but before that, note until now, we have discussed only series with positive terms. So we have discussed the convergence and divergence of series with only positive terms. And we have discussed the alternating series test where the signs alternate. All right. Now we want to basically go ahead and talk about series with positive and negative terms and some other methods of finding the convergence. So before that, let's have a new definition. So we call a series absolutely convergent if it converges absolutely, in the sense a series is summation an is absolutely convergent if you take absolute value of each term and then form a series. It's also convergent. Yeah. So for example, if you take summation n equals to 1 to infinity minus 1 to the power n plus 1 divided by n square, if you look at the absolute value of terms, this is going to be summation n equals to 1 to infinity of 1 by n square, which is convergent using p equals 2. So we are using p series test. So this series is absolutely convergent, right? Now we have a series is we call a series conditionally convergent if it is convergent but not absolutely convergent. Yeah, the example for that is summation n going from 1 to infinity minus 1 to the power n plus 1 divided by n plus 1. Sorry, divided by n. So we have already seen that this series is convergent using alternating series test. However, if you take the absolute value of terms, we'll have 1 by n, which is what? Which is a harmonic series, or p series with p equals to 1 is divergent. So such series are called conditionally convergent series. What is a conditionally convergent series? If they are convergent, but if you take absolute value of terms, they are divergent. So we have the following result, that if summation an is convergent, then, if summation an is absolutely convergent, then it's convergent. Okay. So absolute convergence implies convergence. And let's see how this is going to help us in this series. So if you look at this series, let's try to see the terms, absolute value of the terms. So this sine n upon n square plus 2n plus 1. Absolute value of this is going to be less than equal to sine. So absolute value of sine n is going to be less than equal to 1, right? Because the maximum value sine can have is 1. So this will be 1 upon n square plus 2n plus 1. And this can be seen to be less than equal to 1 upon n square, right? Why is that? Because n square plus 2n plus 1 is greater than equal to n square. If you take 1 over reciprocal of these, the inequality flips. Yeah. So now you can think about this as a series with the positive terms because you're taking the absolute value here. Now notice that summation 1 by n square converges. This implies what? Why does it converges? Because P series with P equals to 2 greater than 1. So this will imply that summation n equals to 1 to infinity sine n upon n square plus 2n plus 1 is convergent. Why is that? Because of comparison test, right? It's comparison test. But being convergent like this means what? This implies summation n equals to 1 to infinity sine n over n square plus 2n plus 1 is absolutely convergent. Because after all, we are trying to establish for this series here, right? So this is absolutely convergent. This implies what? This implies summation n equals to 1 to infinity sine n upon n square plus 2n plus 1 is convergent. And what is the justification for that? The justification is that absolute convergence implies convergence. So the concept of absolute convergence helped you out on how to find out whether the series converges or not. Okay. So now we have the following test to check for absolute convergence. So you have the series summation n equals to 1 to infinity of an. So we want to discuss the convergence of summation n equals to 1 to infinity of an. And we want to discuss the absolute convergence. So what you do is you take ratio of n plus 1 term divided by an. So you're taking an plus 1 upon an. So you're taking this ratio. That's why it's called ratio test. You take absolute value of this and take the limit of it as n goes to infinity. You call that limit as L. Now, based on this L, if this L is less than 1, then this series is absolutely convergent. If this L is greater than 1, then the series is divergent. Okay, not just an absolute divergence or something. It is divergent, period. Okay. And if n goes to infinity of an plus 1 upon an, which is L, is 1, then the ratio test is inconclusive. That means the test fails. Okay. So let's apply this on the problem 1, which was our motivation. So let's apply a ratio test for A. So by ratio test, we need to compute limit as n goes to infinity of an plus 1 upon an. This is going to be limit as n goes to infinity. What is the n plus 1? So wherever there's n, you put n plus 1. Dividing by an is same as multiplying by the reciprocal. So we don't need the absolute value sign because all the terms are positive. So I'll continue here. So limit as n goes to infinity. Now, these terms, so you have this term and this term, that will simplify to give you what? 2. N factorial, n plus 1 upon n factorial will give you what? N plus 1. And that will cancel out with the n plus 1 on the top there. So we'll get, this is going to be simply what? This is going to be simply 2. So this got cancelled with this got cancelled with that. So we have simply 2 by n, right? And limit as n goes to infinity of that is what? That is 0. And hence we get this, which is L, and clearly a L is less than 1. Therefore, what? By ratio test, this series is absolutely convergent. Let's look at the problem B. So we have summation n equals to 1 to infinity of minus 1 to the power n, 3 to the power n upon n square. Again, we'll use ratio test. So we have limit as n goes to infinity of absolute value of an plus 1 divided by an. Let's call this as L. This is limit as n goes to infinity, absolute value of minus 1 to the power n plus 1 times 3 to the power n plus 1 upon n plus 1 square multiplied by, so dividing by an is multiplying by the reciprocal of an, which is n square, minus 1 to the power n, 3 to the power n. And when you cancel the factors, you'll get limit as n goes to infinity. So if you cancel these two guys, you'll be left with 3. So 3. The absolute value will make the minus 1 to the power n and that disappear. What you left out will be n square upon n plus 1 the whole square. Yeah. And that limit you can divide top and bottom by n square to see that that is going to be 3 plus 1 upon 1 by n to the power 2, and that is going to be 3. This is your L, and your L is bigger than 1. Therefore, by ratio test, this series is divergent. All right, so now let's look at C. So summation n equals to 1 to infinity minus 1 to the power n upon n. So we know that this converges, right? This is an alternating series. We have already seen that it converges, but we want to see when we apply ratio test, what do we get out of this? So let's apply ratio test again. So L equals to limit as n goes to infinity, an plus 1 upon an, which is going to be limit as n goes to infinity, an plus 1 is going to be 1 upon n plus 1. I took care of the minus sign because we are looking at the absolute value. So this is going to be 1. So therefore, ratio test cannot say anything. Ratio test fails. Yeah, in this case, ratio test will not tell you anything. In fact, if you take D, let me take a variation of D, summation n equals to 1 to infinity, 1 by n to the power p. So we know that this is P series and it converges if P is greater than 1, diverges if P is less than equal to 1. However, if you can compute an plus 1 upon an, limit as n goes to infinity, this is going to be limit as n goes to infinity, 1 upon n plus 1 to the power p divided by an, which is going to be multiplying by n to the power p, and that is going to be limit as n goes to infinity. Divide top and bottom by n to the power p. We'll get 1 plus 1 by n to the power p, which is 1. So you see, it cannot differentiate in P series. So for P series, ratio test does not work. So when does ratio test really works? Whenever you have factorials, ratio test works well. So if you have factorials, ratio test will work well for those cases. So here, let me finish this off by saying, therefore, the test fails in this case. Okay, so this is a limitation of your ratio test. Now, very similar to the ratio test, we have what is called as root test. Again, the idea is for testing whether the given series is absolutely convergent or divergent. So in root test, what you do is you take an, term an, you take absolute value of that term, you raise it to power 1 over n, you take the limit as n goes to infinity of this, and you call this as L. Yeah, so this is nth root of an, right? You call this as L. If L is less than 1, then the series is absolutely convergent. If L is greater than 1 or it is infinity, then the series is divergent. If L is equal to 1, the ratio test is inconclusive. That means no conclusion can be drawn about convergence or divergence of this. So, in this problem, we'll use root test. So now we are looking at root test. So we'll use root test. Now, question, can we use ratio test in this one? Yes, we can, but it'll be simpler to use root test because we have power n, we have power 2n, and it'll, basically if you're taking nth root, it'll make it easier, right? So so L equals to limit as n goes to infinity of nth root of absolute value of an, which is same as raising to the power 1 over n. So limit as n goes to infinity, n upon n to the power n, 3 plus 1 by 2 to the power n, the whole power 1 over n, right? This is what it means by taking the nth root. Now you'll apply the nth root to both of them. So you will have n, and on the bottom you'll have what? 1 plus, so you'll have n to the power n by n. Here you'll have 1 plus 2n to the power n. Now, if you look at this, this is going to be limit as n goes to infinity of n to the power n, n to the power 1 divided by 3 to the power 1 by n plus 2. Now, as n goes to infinity, the denominator is going to 9 and the numerator is going to infinity. So this is infinity, right? Therefore, since L is limit as n goes to infinity of L is infinity, we say that this series is divergent. So this series is divergent. Now let's look at problem B. So again, you see that you can apply the ratio test here if you want, but it's gonna be very ugly, right? Because you'll have n plus 1 in the inside the power. On top you have n plus 1. So it will make it slightly more clumsy to do this problem. It will be more involving. However, if you use the nth root test, you'll see that it works out right away. So limit as n goes to infinity of an, absolute value of that, to the power 1 over n. This is going to be limit as n goes to infinity of 5n minus 3n cubed upon 7n cubed plus 2, absolute value. So power n, the absolute value of this, to the power 1 over n. And then this simplifies to limit as n goes to infinity, absolute value of 5n minus 3n cubed divided by 7n cubed plus 2. Now you want to find out this limit, divide numerator and denominator by n cubed. So we get limit as n goes to infinity, 5 divided by n square minus 3 divided by n, 3n cubed divided by n cubed, 7 plus 2 divided by n cubed, and as n goes to infinity, this will be absolute value of minus 3 over 7, which is 3 over 7, and this is less than 1. Therefore, the series is absolutely convergent. So again, we want to check these series to see what is happening in terms of. So we already know that C is convergent because of alternating series test. So let's see whether your ratio test can differentiate. So limit as n goes to infinity of absolute value of an. So absolute value of an, the whole power 1 over n. This is your L, right? So you get limit as n goes to infinity minus 1 to the power n. So, well, absolute value of that would be 1. So you have 1 upon n to the power 1 over n. And this limit is 1. So therefore, test fails. Now, let's try to remind ourselves, why is this limit 1? So we'll compute this limit separately. So limit as n goes to infinity of n to the power 1 over n is same as limit as n goes to infinity x to the power 1 over x. And what form is it? It's of form infinity to the power 0, which is an indeterminate form, right? So this is an indeterminate form. So we can apply L'Hopital's rule. So let this be L. So therefore, ln L is equal to ln of limit as n goes to infinity x to the power 1 over x. Now these are sufficiently big, ln is continuous there, so the limit and ln can commute. So we have ln to the power 1 over x, which can be written as limit as x, this is x, right? This is x goes to infinity, ln x over x. Now again, this is the form infinity over infinity. So when you apply L'Hopital's rule, you get limit as x goes to infinity of ln x derivative is 1 over x, and the derivative of x is 1. So this is 1 over x, as x goes to infinity makes it 0. So therefore, we get ln L is 0. Therefore, ln L is 0. This implies L equals to 1, right? So this means that this limit is also 1. Yeah. So therefore, the test fails. Similarly, if you look at limit as n goes to infinity of n to the power p, if you look at this series, summation n to the power p, n equals to 1 to infinity, let's apply the ratio test here. So this is going to be limit as n goes to infinity of, what is this going to be? Limit as n goes to infinity of an to the power 1 over n is going to be limit as n goes to infinity 1 by n to the power p by n. And using the same technique, exactly the same, you can prove, or even otherwise, you can bring the limit inside, right? This is going to be 1 by n to the power 1 by n the whole power p. Now, this is by using the laws of limit is going to be limit as n goes to infinity 1 upon n by n to the whole power p, which is going to be 1 to the power p, which is 1. And this is your L, which is greater than, sorry, which is equal to 1. So therefore, the test fails. So we see the following. The upshot of this discussion is that absolute convergence test of tests like ratio test and root test fail when you apply to P series.